how to compute solubility. For solubility using, well, solubility KSP using molar solubility. Okay, so molar solubility, okay, let's first find out what that means. Okay, it kind of pretty much means that for every mole, in the sense of that molecule in question, there's a certain amount in terms of moles as well that is made from it. Okay, so let's say if you want to find out the molar solubility of let's use Na3PO4, so sodium phosphate. Okay, if we said the molar solubility was like let's say it was quite soluble, it was 0.02, right? Okay, that means for every Na3PO4, like 1 mole about, this amount comes out and forms exactly the Na3, whoops, not Na3, the 3Na plus and the PO4 3 minus. Okay, now this is the part that's important and tricky of it, right? Is that we don't just use this value, we base that value based on the coefficients. Okay, because what we're really saying is that for every Na3PO4, this is the amount here that dissolves, like soluble in water, but that means for every of the amount that's dissolved is going to produce 3 times that amount of Na plus ions, because that's the coefficient here, right? So really we'd have 0.06 here, okay, and the PO4 is going to be coefficient of 1, so 0.02 still. Now, to find KSP, right, the formula for it, okay, is just going to be referring to the products, because usually the reactant is just a solid that's dissolving in water, so it is not included in the equation. So we have I guess you can really just say A, B, and now here's the part that's tricky about it. You want to make sure you have the right coefficients of it. Okay, that's why I use Na3PO4. I would say we can just say this is X and this is Y. Okay, because if you had more complicated types of like let's say we actually wanted calcium phosphate, that's a good one. Ca3PO4 2, right? That was a really good value, I mean really good number, because the coefficients for each one, you still have 3 calciums, yes, but you would have 2 phosphates, meaning that the Y in that case would be 2. So if you want the KSP, actually, let me use each one. The KSP for Na3PO4, okay, it would be Na, the concentration of Na, which is what we have here, because that's the molar solubility, because they usually just give a value like in molarity, and it'll be to the power of 3, and then PO4, I don't like how I wrote that, Na plus, there we go, and it'll be to the power of 3, and a concentration of the phosphate ions to no power, because exactly as you see here, it's a 1-to-1 ratio. And if you do the KSP for calcium phosphate, okay, this is where you would have, yep, the calcium still. This is going to be to the power of 3, but the phosphate, because now actually there is a coefficient of 2, it would be PO4 3 minus, okay, to the power of 2. That, plug it in, okay. So exactly, if we did this example for KSP for the Na, it'll be 0.06 to the power of 3 times 0.02. So the KSP for this would actually be all the way 1, 2, 3, 4, 5, 6. So it'll be 4. Let me write in a different color. That one with these made up numbers, just to be able to write it down actually next to it, 0.06 cubed and 0.02. It would equal 4.32 times 10 to a negative 1, 2, 3, 4, 5, 6. Okay, that is a KSP value, and KSP kind of works the same way as Ka and Kb, just acid bases. Pretty much just the same, that when put in water, it's almost like not going to dissolve, or just not that significant. It is considered like a weak dissolving, like you're not really weak acid, weak base, but more so that you always have precipitate, because all that solid is not going to dissolve in the liquid, because it prefers, based on the KSP, to be still in its solid state. Okay, so now if we do the same thing for KSP for the calcium phosphate, right, you'll actually notice that even though it's going to be the same amount of I guess the 0.2 that may have dissolved from it, okay, is going to be, now this value is going to be 0.06, okay, cubed. But now remember, because of the coefficient, it's going to be double that amount, so it'll be 0.042, okay? And then when you multiply that together, you get 3.46 times 1, 2, 3, 4, 5, 6, 7, 10 to a negative 7. So exactly. That's why it's very important to just do these steps, because at first glance you wouldn't really be able to tell what that KSP value would be. So technically speaking, right, the sodium phosphate is more soluble than the calcium phosphate, which also would make sense as well, considering that like when you think about it, a lot of things that are with sodium are quite soluble. This is just theoretical though. I know there's actual values for it, but theoretically speaking, if the same amount of the solid became like the whole moles per liter, then it's usually the one that has the least constituents in total, because technically 3 plus 1, because that's going to be the coefficients, that'd be 4 versus 5, is the one that's going to be more soluble, because it kind of implies that it's going to be less things multiplied, because you're multiplying tiny numbers, and less things being squared or cubed and such. So that is a summary of how you can find KSP from molar solubility. Let's see how we did. They chose something easier. K, silver bromide, is just 1-to-1 ratio. So if they said the molar solubility was 5.71 times 10 to a negative 7, you just be multiplied number twice by itself. 5.71 times 10 to a negative 7 times 5.1 times 10 to the negative 7, and that would be the KSP value you get. And they said you don't want to include the AgBr, the silver bromide itself, because it's solid. So exactly, that's what we have here as the formula, KSP AXBY. So this is correct. Okay. And now let's move on to question 10. Okay. And now